start recording. I will do an intro. And can you guys see me or no?
Yeah.
Okay. So, Eve, are you ready to go?
I'm ready.
Awesome. Well, everybody, it is a treat to have Dr. Eve Vavagiakis, who was a Provost Diversity Fellow and PhD candidate in the physics department at Cornell University, but she needs to update her webpage because she's now a PhD. She is now an official postdoctoral. She is now a postdoctoral scholar, I believe, and we're going to learn more about her research in cosmology, in particular, looking at distant galaxies and using the Atacama Cosmology Telescope, the ACPOL receiver, and looking for both the thermal and kinematic Sunyaev-Zel'dovich effects. And fun fact for Eve, she may not know, I had two advisors in graduate school. One was Alexander Polnarev, who's a Russian scientist, and his PhD advisor was Yakov Borisovich Zel'dovich. And he was an amazing scientist who would say really funny things that I learned about, like when I was trying to do too many things at once. Alex would say in the name of Yakov Zel'dovich, he would say, Brian, 9 women cannot have baby in 1 month. And I never really knew what that meant. But anyway, it is such a delight to have such an erudite scholar joining us today, talk about her research. This is an episode of the podcast that I call Journal Club. You get to see what real live scientists do when they're in the laboratory and doing analysis, and really work on new models of how the universe works. And there's no one better to learn about than Dr. Eve Vavagiakis. So Eve, it's such a pleasure and a delight to have you here. Congratulations again. And I can't wait to hear today's presentation.
Oh gosh, thank you so much for that wonderful introduction. It's wonderful to be here digitally with all of you. And yeah, I'll be talking about my work measuring the Sunyaev-Zel'dovich effects. This work was the effort of many of us here at the Cornell Physics and Astronomy departments, as well as the ACT collaboration. So thank you to everybody who is a part of it. I'll start with some overview of the SE effects, and of course we're looking at the cosmic microwave background here. So this is relic radiation from about 380,000 years after the Big Bang. And it's highly isotropic, but it contains these anisotropies that we see when we boost our color scale and look at these small fluctuations in the light. And today we'll be talking about secondary anisotropies, and these are what we call the fluctuations that were encoded after the surface of last scattering, when the photons from the CMB are traveling through the matter in our universe before reaching us here on Earth today. So in this image here, you can see how we're looking back both in time to the CMB and through structure to the CMB. So these early fluctuations encode information about the universe as it was early in the universe's history, but also what happened to it as it passed through all this data. This is from the SDSS, BOSS SDSS survey, and that's actually the data set that I'll be talking about in our work in this talk. So these secondary anisotropies, you can even see some of them by eye. Here are some little submaps from Sigrid Ness's paper in covering the ACT dataset that co-adds data from Planck with maps from ACT into these map products that we use to measure the SE effects. So you can take a look at these and see little astrophysical sources popping up as bright spots, as well as shadows of galaxy clusters appearing. These shadows of the galaxy clusters, that is the Sunyaev-Zel'dovich effect that I'll be describing in the next few slides. So secondary anisotropies contain rich astrophysical information that we're interested in studying in its own right to learn about the physics of the structures in our universe. And they can also contaminate our primary anisotropy measurements. So if we're looking at excellent constraints like we're doing right now in the field and pushing for in the future for cosmology, we need to be able to constrain these, understand them, and then remove them when appropriate for making our measurements. These panels show the 3 frequencies of the co-added data set with ACT and Planck data. These are at about 100 gigahertz, 150, and 220 gigahertz. You can see that ACT, having this larger mirror, enables these high resolution measurements that you can see these clusters appearing by eye, and they're absent in Planck. So each of these panels is the same little patch of sky, and you can't see those galaxy clusters in Planck, but when you co-add them, you get the benefits of both of the experiments. And so the center panels are the co-added data that we then work with for our measurements in this paper that I'll be discussing later. And I also like to point out that in the SE effect, and by the way, I'm assuming you can see my cursor moving. Is that a correct assumption? Yeah, okay, great. In the SE effect, in the thermal SE effect, you see a null at around 220 gigahertz. And I think it's neat, just by eye, you can see those little galaxy clusters disappear at that frequency. So I said the word cluster a whole bunch. I'll be talking about galaxy groups and clusters and halos a lot over the course of this talk. So when I'm talking about these are gravitationally bound collections of galaxies. There's no sharp distinguishing cutoff between groups and clusters, but clusters are more massive than groups and contain more galaxies. These structures grew out of initial fluctuations in the very early universe, and they contain both dark matter and baryonic matter. You can think of them in terms of this assumed profile where you have a higher density in the center and then it falls out with some characteristic function of radius. And recent measurements have found that the baryonic content of these halos is less than we would expect. This is the missing baryons problem. We think that this baryonic matter is lying more in this warm, hot intergalactic medium. And so we're interested in studying the baryon content of these galaxy group and cluster halos. We're able to measure the spatial distribution of the gas in these groups and clusters using the SE effects. And so in this talk, I'll talk about how we could potentially use the TSE effect and the KSE effect to learn about the baryon content of groups and clusters. And when we learn about that, we'll learn more about where the matter in a universe is lying. The KSE effect is also going to tell us about how these structures are moving around in the large scale structure of our universe. And we can also gain insight into the feedback mechanisms that are driving the evolution of these galaxies, so we can learn about the astrophysics at play there. So the Sunyaev-Zel'dovich effects, again, are secondary anisotropy. They're caused by the CMB photons coming in, inverse Compton scattering off of the electrons that are present in gas, especially that's grouped into these clusters and groups. And in these halos, you can see them as a shadow at certain frequencies that we observe at these smaller arc-minute scales. The reason we see a shadow is because if you plot the blackbody spectrum of the CMB in blue here, and you look at what happens to it when a photon comes in and shifts that blackbody spectrum up because of the energy that's in the electrons that scatter these photons, the spectrum is shifted such that if you observe at about 220, like I pointed out in that panel earlier, you see no change in the intensity of the CMB in that spot. But if you look at frequencies below about 220 gigahertz, you see a decrement. This decrement is why you've been seeing shadows plotted. If we were to observe above about 220 gigahertz, you would see an increment instead. So the thermal SE effect has a temperature shift, which is proportional to the integrated electron pressure along the line of sight. You can express the change in temperature of the CMB due to the interactions with this gas as a function of observation frequency times the Compton Y parameter. You can think of the Compton Y parameter as being an expression that gives you the number of photon scatterings in the gas times the energy gain per photon scattering. It takes into account the Thomson scattering cross-section, as well as the line of sight integral over the electron number density and the temperature of those electrons in the gas. It's proportional then to the halo optical depth, which is the line of sight integral over the electron number density, and takes into account the Thomson scattering cross-section. You can think about optical depth as being a measure of how likely it is that a photon is going to be scattered by that gas. So if you have an optically thin gas and tau is smaller, then you'd have a lower likelihood of interaction. Whereas if you have an optically thick gas, you're more likely to scatter those photons. When we look at Compton Y, it's a proxy for the mass of the halos. So larger Compton Y, larger halos tend to be more optically thick, larger tau. So that's how things scale there. We're also interested in studying the kinematic SE effect. This has a temperature shift now, which is due to the bulk electron line of sight velocity rather than the temperature of the gas. So it has a proportionality to the line of sight momentum of the gas that we're looking through. You can express the temperature change due to the KSE effect in terms of tau in this approximation. Again, tau is the optical depth of this gas. and the velocity. So a photon from the CMB comes in, interacts with that gas that's moving around in the large scale structure of our universe. If the gas is moving away from us along the line of sight, you'll see a redshifted photon. Whereas if a photon comes in and interacts with gas that's moving towards us, it'll give it a kick in energy due to that velocity, and we'll see a blue shifted photon. These lines towards one another show the pairwise motion of these galaxies. In this talk, I'll be discussing the pairwise estimator approach to measuring the KSE effect. There are a number of ways you can measure velocities, but we look at this pairwise motion, which tells you how quickly these objects are moving towards one another. If you look in different frequencies, this is advantageous to measure the SE effects. So here's a plot of the TSE effect in black, the KSE effect in red. And here the KSE effect has been scaled by a factor of 10, so you can see it better. It's a very small effect. The fact that we're taking temperature differences to get at this pairwise motion helps us in measuring it because it is averaging out due to the subtraction of the two different temperature signals, the TSE effect and other contaminating factors like dust. So I'll talk about that more later. It's also a statistical method, which means if we have many galaxies to look at, we can improve our detection. But measuring in multiple frequencies will help us both in constraining the SE effects themselves, as well as removing from contaminating sources like dust. Okay, so why are we interested in studying this at all? This plot shows the pairwise velocity of those galaxies, like I was talking about in the last slide, as a function of the separation distance, or how far they are from one another. You can see there's a peak in this velocity at separation distances between about 20 and 40 megaparsecs. And this gives us an indication that on average, these galaxies are moving towards one another due to the attractive force of gravity. Now, we're interested in making careful measurements of the pairwise velocity curve because this gives us insight into open questions in cosmology today. For example, we know that massive neutrinos affected the growth of structure in our universe. In the simulation, you can see what happens if you put no mass in neutrinos. You get this clustering of matter due to gravity that creates these overdense regions in red and underdense regions in blue. But if you put some mass into neutrinos now, these little, I call them mass bandits, can run away with some of the mass early in the universe's history because they're free streaming relativistically. And so they wash out these overdensities and underdensities, and you see kind of a washed out version of what you see on the right-hand panel. And so measurements that are sensitive to the large scale structure of the universe can place upper limits on the sum of the neutrino masses by saying how much mass was ran away with early in the universe's history. So we're interested in doing this. You can see how the pairwise velocity curve will change if we have different sums of masses in the neutrinos. We're interested in learning about this because it's an open question in the neutrino standard model. We don't yet know if the third mass eigenstate of the neutrinos is the heaviest in the normal hierarchy or the lightest in the inverted hierarchy. And by placing upper limits, we'll have the potential, and we're likely to determine the mass hierarchy with cosmological measurements in the next few years. But this will also give valuable information to laboratory experiments because the measurements we're making are independent from the lab experiments that are happening on Earth. And they will also help interpret the lab experiment results, such as neutrinoless double beta decay experiments, which are looking for whether or not the neutrino could be a Majorana fermion. And if the neutrino was a Majorana fermion, there are interesting implications involving CP violation that could enable this leptogenesis early in the universe's history that might explain the matter-antimatter asymmetry that we observe in the universe. It's a large open question in physics today. So there's a lot to be learned once we can pin down the sneaky neutrino mass a bit better. We can also start answering some questions about dark energy, potentially. You can see here how the pairwise velocity curve is sensitive to these parameters that I'll describe on this slide with very many arrows. So we know that the universe is experiencing this accelerated expansion, but we don't know why. In lambda CDM cosmology, we describe this dark energy with this negative pressure that is driving this expansion. We can write down this equation of state for dark energy and parameterize it in terms of these parameters W0 and WA. In lambda CDM cosmology, W0 is taken to be -1, and there is no time dependence in dark energy, so WA is 0. If we find by measurements such as this one that we have more consistent measurements with a time evolving kind of dark energy, or if W naught is not equal to -1, then we have some hints that we might not be dealing with the lambda CDM cosmology that we know today. We can also look at the matter density contrast in our universe and think about general relativity. We can look at the early fluctuations in the density of our universe and how they evolved over time. This factor here is the growth factor, and we can write down the growth factor as it evolves in GR in terms of this logarithmic linear growth rate f, where you take the logarithmic derivative of the growth factor, and you can approximate that in terms of the matter density to this growth index gamma. The point here, I'm glossing over all the details, of course, but the growth index in general relativity is about 0.55. So if we find some inconsistency with this number, we might have a clue that perhaps some modified gravity model might explain the physics of our universe better than GR. So we can test general relativity by making these measurements of pairwise velocity. So I'll talk about measurements with ACT in this talk. ACT, of course, is a 6-meter CMB telescope on Cerro Toco in Chile, right at the same site that the Simons Observatory is being built. It's currently observing with TESs, and the data sets that I'll talk about today have been co-added with Planck. So I'll be focusing on this paper that we are now just about to publish in PRD. We're at the end of the revisions. It's entitled The Atacama Cosmology Telescope, Probing the Baryon Content of SDSS DR15 Galaxies with the Thermal and Kinematic Sunyaev-Zel'dovich Effects. It's one of 2 companion papers. So the other companion paper is Califoot, Gallardo, and myself et al. And this is now focusing on the pairwise kinematic SE effect. So I'll present a little bit of the pairwise KSE measurements in this talk and discuss the optical depth estimates that came from those. But for the details of the KSE work, I encourage you to check out this paper. There's a rich heritage with ACT measurements for these SE measurements. Of course, ACT, the South Pole Telescope, and Planck have all made TSE and KSE measurements in CMB datasets. If you're interested in more on TSE stacking and dust reconstruction and the types of methods that we're doing in ACT data, you can look at Brittany Fuzia's paper on the SE-based masses and dust emission from IR cluster candidates in the Sheila survey, Megan Grala's paper on SE effects in low-frequency radio sources, and Sue et al. Covering the redshift distribution and properties of ACT-selected dusty star-forming galaxies. For the pipelines that we've been working on, there are these early results that formed the path that we've been going down. Hand et al. In 2011 wrote on a detection of TSE effects in ACT data, stacking on a matched filtered CMB map with about 2,600 galaxies. It's really cool to look back and see how many galaxies we were working with just some years ago and how many more we have now. So in the paper that I'll be talking about today, we have over 340,000 galaxies to work with now. In 2012, Hand et al. Reported the first measurement of the KSE effect using ACT data. This is the pairwise momentum curve now. So for the rest of the talk, I won't be plotting pairwise velocity like I showed in the previous slides, but instead we have pairwise momentum. We're interested in measuring optical depths of these halos because we want to get to pairwise velocity in order to do the cosmology that I just advertised. And in order to do that, we need to break the degeneracy with tau. So right now we are working with momentum. You can see there's a dip here. We have better signal to noise, so the dip becomes more apparent in the next few slides, but that dip corresponds to that peak in velocity, which again, these objects are moving towards each other at these characteristic scales. So this first detection of the KSE effect used the pairwise estimator that I'll be talking about. And in 2017, Francesco Di Bernardis led our effort in measuring the KSE effect at higher signal to noise in ACT data using BOSS DR11. This paper was the first time that I measured the TSE effect using stacking and then looked at how those measurements of optical depth compared to the KSE optical depth estimates. And we found the results encouraging. I'll talk about them a little bit more, but that's what paved the way for the current measurements. And finally, in this paper advertisement part of the talk, I'd like to point your attention to Emmanuel Sean et al. And Stefania Amadeo et al. Because they're doing complementary measurements of TSE and KSE effects in ACT data using the same maps that we're working with in the paper I'll talk about today, using a different data set from BOSS. These are the CMAS and low Z samples of galaxies. And they use a velocity reconstruction approach. So it's a different estimator than the pairwise estimator, but it's still measuring the KSE effect. They have a slightly higher signal to noise measurement, and it's complementary to our efforts. So we'll be working together using different KSE estimators moving forward. Stefania's paper also focuses on gas thermodynamics and presents the dust corrections that we use in our work in order to estimate some of this dusty emission using Herschel data. Okay, so what are we doing? This is an overview of the measurement principles that I'll be talking about in kind of the simplest form. So we have a CMB map, thanks to everybody at ACT, making great observations and map products for us to use. We also have an optical survey. So we're using data from BOSS. This tells us where the galaxies are. These galaxies are luminous red galaxies. We take them to be proxies for the centers of group and cluster halos. This is a good assumption, it turns out. And they tell us the position, the luminosity. The higher luminosity LRGs trace higher mass halos. So there's a relationship between luminosity and mass that we can use. And again, remember that scaling, higher luminosity, higher mass, larger Compton Y, larger optical depths in general. And so then we also have the redshifts, and we use this in the pairwise estimator in order to reconstruct, or not reconstruct in the sense of the velocity reconstruction method, but still do a geometrical argument in order to give the pairwise momentum of those galaxies. So, okay, we know where they are, so then we can stack on them, which means we draw a little box, take a submap around each of the galaxies and average them together. This is the TSE stacking. When you do that, you see the shadow show up in this stacked submap. So this is one of our luminosity bins, which means we have a selection of galaxies above a certain luminosity threshold, and you can see the SE effect appear by eye. We measure the TSE signal using aperture photometry, which means we draw a disk and a ring, take the average in the disk minus the average in the ring, and that gives you the TSE signal associated with that sample of galaxies. For the KSE estimator, we have the positions, again, associated with the sources as well as their redshifts. And we can take the same filter, aperture photometry filter, and associate a temperature in the position of that tracer galaxy, and then reconstruct their pairwise momentum. Okay, so we have a TSE measurement. We want to get to optical depth. In order to estimate optical depth from our Compton Y measurements, we use this hydrodynamical simulation from Battaglia in 2017. This gives a relationship between the optical depth tau of the gas and the Compton Y of the gas using a variety of different subgrid physics models. We take the model that we think best describes our sample, and we go from Compton Y to optical depth. The maps we're working with are either in Compton Y already or they're in temperature units. And if they're in temperature units, we use this relationship, which depends on observation frequency, to get to Compton Y. So eventually we get to optical depth from the TSE, and we can compare it to the optical depth from the KSE. So this shows how we did that in 2017. We had a smaller overlap with a smaller map, and we used the DR11 sample instead of the DR15 that we're working with now. This gave us about 68,000 sources overlapping with the map, and you can see them in green. This is a histogram showing the number of sources per redshift bin. You can compare it to the previous results in Hand et al. And the smaller sample of galaxies that we had to work with back then. And this again pales in comparison to the many hundreds of thousands of sources we have now, and things will only continue to improve in the future, which is exciting. So this gave us a 4 sigma measurement of the KSE effect. We used the pairwise estimator again. These data points are what we measured. They're plotting the pairwise momentum of the clusters as a function of their separation distance. And then we do a fit with a model. This is the black line that you're seeing. And that fit returns optical depth as a free parameter, setting the amplitude here. So once we have that fit, we have tau. And then we can compare tau from TSE versus tau from KSE. And in an ideal world, we'd love to see these data points on a straight line with a slope of 1. We fit to the independent data points in dark blue and found that the slope was consistent with 1 within our relatively large uncertainties. So today we have larger maps. These are the ACT and Planck co-added maps. They contain data from ACT taken between 2008 and 2018. And we're co-adding that data with data from Planck in the 2015 and 2018 releases. I mentioned previously, but this covers 3 frequencies at 100, 150, and 220 gigahertz. And in Sigurd's paper, we also identify 4,000 SE clusters and over 18,000 point source candidates. So this figure shows 2 of the frequencies that are available. These maps are publicly available on Lambda for anybody to work with. And it shows the Planck data in black and white, and then the ACT observation regions in the colored outlines. And the contours that are in dark red show the deepest regions of ACT observations. These are, again, deep regions of ACT observations plotted in this map here. We call them, they used to be BOSS North, but I think now they're just BN and D56, which used to be Deep 56. So these are just deep observation regions. And in Matt's paper, we describe how we can component separate these maps using an internal linear combination approach to separate out things like Compton Y from the CMB and make maps of CMB plus KSE. These 2 products are what we used in our work to measure the SE effects. We use Compton Y for the TSE measurements and CMB plus KSE for the KSE measurements. And so these are the regions that are available for those maps. So now this is from our paper showing a cropped version of the co-added map overlapping with our SDSS sample. So the blue points overplotted here show the entire sample of galaxies that we used after a series of cuts. We did a noise map cut, so we're focusing only on the overlap with the deepest regions, and those are plotted in purple here. We also did a galactic plane mask using the galactic plane mask from Planck that was used in the 2015 Compton Y map production. And we did a point source mask using the same point source masks that were used in other ACT analysis before. The blue shows overlap with that deep region D56 for the component separated map analysis. And the green shows overlap with the BN region, again, for the component separated map analysis. So because these deeper regions are a smaller area, we have slightly fewer sources in those regions. So I showed this histogram previously and said that it pales in comparison to our sources here. So that's what you can see in this histogram. Now in blue, we're showing the full sample that was available to us, as well as the selected sample in the dark blue step, and comparing it to what we had to work with in 2017. On average, we had sources that, or LRGs that had redshifts of about 0.5. So we worked with the 150 and 98 gigahertz co-added maps, as well as the component separated maps. And after the cuts, we had 343,000 sources covering 3,700 square degrees of sky. This is the table that summarizes the luminosity bins that we worked with. So we had 5 cumulative and 5 disjoint luminosity bins for the TSE work. The specific luminosity cuts shown here were chosen based off of the 2017 work for consistency. And then we chose 3 equally spaced bins for the joint analysis between the KSE and the TSE work. And so we chose these bins to have about 100,000 sources per bin. The asterisks here are showing which bins are analyzed between the two companion papers. And then these higher luminosity bins were included for the TSE analysis because they'll have the higher signal to noise measurements of the TSE effect. But the number of galaxies per bin is too small for high signal to noise measurements of the KSE effect. So they weren't included in the KSE measurements. So this table shows luminosity selection cuts, the corresponding mass thresholds and stellar masses of those bins, as well as the number of sources per bin, average luminosity, average redshift, And you can see that there are fewer sources per bin, like I mentioned, for the component separated maps, otherwise known as the DR4 ILC maps, than there are in the co-added maps. So I'll briefly talk about the Pairwise KSE estimator on this slide. It's a statistical method, again, to extract the KSE effect. We use an aperture photometry filter with the disk radius chosen to be 2.1 arc minutes based on the redshift of our sample. And this gives a temperature signal associated with each source. Again, taking the average of the disk minus the average of the ring. We know that this temperature signal is proportional to the line of sight momentum of that gas. And then we use the redshift information from our catalog to plug into this geometrical factor C, which gives us the pairwise velocity as a function, or pairwise momentum, excuse me, as a function of the separation distance. And so the pairs are coming out of this subtraction. So you have I and J. These are summing over different pairs on the sky. And that difference here is what is averaging out contamination from TSE effect and dust. So you sum over these pairs of galaxies that share similar separation. Each one of those separation bins is one of those data points plotted in the pairwise momentum curve. This text here is discussing how we selected our submaps to be 18 by 18 arc minutes. And we worked with originally a pixel size of half an arc minute until we repixelized to 0.1 arc minutes per pixel, and then we projected to a coordinate system centered at the galaxy center position using pixel. So these are some of those results. The pairwise momentum is plotted as a function of separation distance for the 3 different maps studied. The black points are the component separated CMB plus KSE maps. The blue points are the component separated, or I'm sorry, the co-added 150 gigahertz map. The orange are the co-added 98 gigahertz map. And each of these panels is for a different luminosity sample. So this is the higher luminosity bin, and then this is the lower luminosity bin, but these are cumulative, so the lower luminosity bin is for the full sample. So when you're looking at this, you might notice that the uncertainties are larger for the bottom panel. And this is because when we're dealing with a smaller number of sources, since it's a statistical method, we have a larger uncertainty. When we have a higher number of sources, those error bars are smaller. However, you can also notice that the dip in the full sample is a bit shallower than the dip we see at the higher luminosities. And that's because we have a higher signal associated with these higher luminosity, higher mass sources. So there's a balance here between the luminosity of the sample and the number of sources per sample. So altogether, we made a 5.4 sigma detection of the pairwise KSE effect. By doing fits to these data points, we obtain estimates of optical depth. And you can see that here, tau comes into play, as I mentioned before. This plot shows the different bins studied with that effect of larger uncertainties with smaller numbers of sources. Overall, we were seeing consistent values across the maps. So now we wanted to compare tau from KSE with tau from TSE. In order to get there, we stack on these submaps. Each submap plotted here is a different luminosity bin. The top 2 rows are the 98 gigahertz coad. The bottom 2 are the Compton Y. Compton Y is the component separated map. Note here that this is negative Compton Y because I wanted to just show intuitively by eye that it's a shadow, but Compton Y is a positive quantity. So this sign was flipped to plot these submaps. We did the same aperture photometry with the 2.1 arc minute radius as the KSE measurements. And this was an improvement over our 2017 work in which we used a matched filter for the TSE measurements, but not for the KSE measurements. So now that's consistent. And we estimated the uncertainties associated with that quantity using a jackknife error bar estimate method. The little clouds that I drew along these names of luminosity bin indicate the joint TSE and KSE analysis. And you can see by eye that the higher luminosity bins, which are on the left, have a higher signal to noise. Even just by eye, the shadows are darker than if you look at the lower luminosity bins in which the SE signal almost disappears just to your eye. It's still there, but it's smaller signals to noise. We had cumulative bins as well as disjoint bins, and the disjoint bins are independent bins from one another, so they don't share sources in common. And those are plotted as the second row of stacks here. This is the 150 coad, and I'd like to note that you can see this central bright spot appearing, which we attribute to dust, and you can see it by eye in many of the bins appearing at small scales within that disk that we used for aperture photometry. And so we wanted to investigate that a bit further. This plot shows only the 150 gigahertz co-added data in the paper. You can see this for every map that we studied. It gives the radial average of the stacked submaps. So this is the center of the submap, and then you just run a radial average out and normalize to the average value within the annulus. The black dashed line is the disk radius, and the solid black line is the annulus radius. And then we would expect the SE effect to just continue to have the strongest decrement or highest signal right at the center of the submap. But we are seeing here, just like in the previous slide, this central bright spot appearing as an increment in temperature at the beam scale or below. So we were considering whether or not our Herschel dust estimate that we applied later was sufficient to remove this contamination. And in order to study that, we have this plot here. This is showing the TSE signal as in temperature for the co-added maps, scaled by a frequency dependent factor to better compare the two frequencies. The frequency dependent factor is written here in the text. So the filled circles are the raw results that we just get from stacking. The blue is at 150, the orange is at 98. The triangles are what happens after we correct for dust using Herschel data. So we stack on the same positions of these galaxies in 3 different observation frequencies and Herschel data in order to estimate the dust emission that's present there. Then we correct for that. The details are in Stefania Amadeo's paper. And then I cut out just the central beam scale of those submaps in the open circles to see what we would see. And this confirmed that within 1 sigma of our Herschel corrected numbers, this just complete removal of the central section of the map didn't bias our results past 1 sigma. So we didn't proceed with including this. We would also need to carefully correct for that if we were to remove that central region, because that's where we expect a lot of our TSE signal to be located anyway. So in the future, it might be important to keep an eye on this, but with our current level of uncertainties, we don't need to proceed with removing the rest of that contamination. This table shows the dust estimates from Herschel data, and you can just see that the numbers are small. So we are dealing with temperature signals that are, I don't know, here's just a number 0.8. And here for that most luminous bin, you can look at here and you have a dust correction that's 0.04. So it's a small change, and that's why you see the triangles being quite consistent with the filled circles in this plot. This table shows the TSE results in summary. Each of the luminosity bins is written down along with the TSE signal and temperature units and in Compton Y for the 2 co-added maps, as well as the native Compton Y units for the component separated map. So we found that the measurements were consistent across the 3 maps. And I think it's probably easier just to look at the plot version of that table. This shows the disjoint bins as well as the full sample and plots Compton Y and signal to noise for each of these bins. You can see now by eye that they're consistent, and you can see that our highest signal to noise measurements were in the higher luminosity bins, as we would have expected. So now we have Compton Y and we want optical depth. So this is where we employ that hydrosim relationship. This gives a relationship between tau, optical depth, and Compton Y. We choose the parameters that best describe our sample based on the redshift of that sample. And then we report that data in this large table. So this table gives the luminosity bins again. This table, the beginning of the table is the 150 gigahertz coad, the 90 gigahertz coad, and the component separated map on the bottom. The second column is theoretical tau, and that's the estimate that we made based on theory, assuming a Navarro-Frank-White profile. This is telling you how we expect that the density and the content of both baryonic and dark matter to fall off with radius if the baryons were to trace the dark matter in that halo. So in that case, you write down your theoretical tau, use the estimate of the mass of these halos based on their tracer galaxies, and come up with how much optical depth we think we have within our 2.1 arc-minute aperture in the aperture photometry. And so that's our theoretical tau that we can compare our observations to. Then we have our estimated TSE tau, a systematic error bar associated with the uncertainties on the physics models that are present in the hydrosim relationship, and the statistical uncertainty that's present in the TSE measurements just propagated through to tau. And then we have FC. FC is the fraction of theoretically predicted baryon content as observed by the TSE measurements. So you can think of it as just taking tau from the TSE divided by tau from theory. So if you had 1, that would mean we see exactly the theory number. Then we report tau from KSE. These numbers are presented in Califoot et al. From the KSE estimator. And we do the same thing, just taking the fraction tau KSE over tau theory, and that gives you FC. So here's the plot version of that table. Now we're just plotting the 3 disjoint, so independent bins of sources that were both studied in the TSE and KSE work, as well as the full sample. FC is what's plotted on the y-axis. This is the measurement over theory. And the full circles give the TSE results. The open circles give the KSE results. So this is where we can start thinking about how much of this optical depth content or equivalently baryon content we're seeing compared to the theoretical predictions. And because our uncertainties are large, we're not able to put tight constraints on this baryon content, but with future higher signal to noise data, we will be able to. Right now, we're seeing between about 1/3 to all of the theoretically predicted baryon content. And we find that the TSE and KSE results are in agreement in 2 out of the 3 bins that are co-studied. But in this higher luminosity bin, we see a difference at 2 to 3 sigma. We're interested in understanding that a bit better. We can plot this in a different way. This is now plotting tau from the KSE measurements against Y from the TSE measurements. And this removes the hydrosim relationship from the TSE measurements. Instead, we can overplot that hydrosim relationship in this green line in order to just compare theory to experiment. Our data points are plotted with the typical colors, where black is the component separated result, orange 90 gigahertz, blue 150. And these are, again, only the disjoint bins that I compared on the previous slide. You can see that the observations agree with the theory within the 1 sigma error bar in the theory presented as the shaded region. And again, that highest luminosity data point is low in the KSE. What we would like to do is expand out this high luminosity data point into sub bins so we can plot more data points, because there's, of course, a great deal of correlation between the maps that were used since they're the same data products. So we can't do that because right now we have about 100,000 sources in this L79 bin. If we were to subdivide it into fewer numbers of sources, the high signal to noise we have on the KSE would go away because we need large numbers of galaxies in order to make this statistical measurement. So in the future, we'll have larger data sets to work with, and we'll be able to have more data points in mass to plot. And so we can look at if there's actually a mass-dependent relationship here, or if this is just kind of an outlier, because it is only at 2 to 3 sigma. So that's something that we are interested in following up with now and are currently working on for future data sets. Actually, before I go to the systematics discussion, I do want to mention that this is exciting because it's the first step towards an empirical Y-tau relationship. We currently have only been working with theory models. We have simulations we can do based on different feedback mechanisms in galaxies to tell us how these things are going to evolve. And this is really a first step towards using just measurements alone in order to feed back, no pun intended, into the feedback models and inform theory with measurements and see how we're doing in terms of our theoretical predictions there. So in the future, it'll be exciting to see what comes out from that. Okay, so now systematics discussion. The Herschel dust corrections that we employed partially address the source galaxy emission, but as we saw, there's some residual dust contamination. Right now, it's less than 1 sigma, but in the future, it could be important. So it'll be something to keep an eye on for future stacking efforts. We used a galactic plane mask for the synchrotron emission, which is sufficient for our purposes. But future work is going to improve on this by modeling and removing this dust and synchrotron emission from the tracer galaxies. We'll be able to do this with high frequency measurements and multi-frequency measurements. And we're going to make really great constraints on the dust and synchrotron emission in the future for both this kind of science effort and also other science efforts. In this work, we also estimated a 2 halo term. This is the correction to the assumption that we're only seeing 1 halo per aperture. In fact, there could be some additional halo that's present in that aperture. Right now, that contribution is again found to be less than 1 sigma, but in a similar vein to everything else I keep saying, it's going to be important to correct for with higher signal to noise work. The details of the 2 halo correction are also in Stefania Amadeo's paper, if anybody's interested in that. And in the future, it will be important to carefully consider the mass luminosity relationship that we looked at in this work, as well as to understand the samples in your simulations. So we could improve upon our comparisons to SIMS by expanding the mass range in the simulations lower, since we dealt with so many lower mass groups than we did high mass clusters. So both correct overlap between the samples used in measurements to theory, as well as uncertainty propagation in the samples between mass and luminosity are important to consider for the future. So speaking of the future, SO is happening. I'm pretty sure you're all making that happen right now with epoxy and other things. The work that I'm talking about here is forming the basis of the SO Pairwise KSE pipeline for measurements with the Large Aperture Telescope. We have the KSE code live, and the TSE code is coming up. I've been a little distracted with my thesis, but now I'll be able to get that live online. Of course, the pipeline has been validated on real ACT data since it was just published on and discussed in this work. And in these papers, we did checks using some simulations of noise for null tests. And we'll be continuing to test the pipeline and refine it over time for SO. So in the next steps, we're going to be exploring that trend of luminosity and hopefully one day using the TSE measurements directly for looking at pairwise velocities, which will be really exciting because we'll start to probe neutrino mass and dark energy and other items of interest. And we'll also have an empirical y-tau relationship that we can compare to simulations. So that's all restated on this slide, essentially. I think on the next slide, yes, I have some constraints, some predictions. These are a little bit older, but they still show how much better we're going to be doing in the future using KSE information from a CMB S4 effort, combined with information from Planck and from lensing in red. These constraints are now drilling down on the parameter space of the sum of the neutrino masses and the matter density and dark energy equation of state parameters. This plot from the CMB S4 science book shows how much better we're going to do when we add in KSE information to these clustering and redshift space distortion predictions using DESI. So that's the blue line. We'll be making better measurements of sigma 8 and the logarithmic linear growth rate f. And that's without an informative prior on tau. So now tau is not just the optical depth associated with a galaxy halo, but is the optical depth period, optical depth to the photons that we're studying. And if we do make better measurements of tau from independent sources, we'll be able to improve our KSE measurements. So this is an overarching trend where for better KSE measurements, pairwise KSE measurements, we need optical depth information. And in the future, for other KSE measurements, we'll still need optical depth information. So hopefully the TSE effect will be useful there. And now, I don't know what time it is. Do I have a little bit more time to plug CCAT?
Yeah. It's 11:56, and we're not on a like super schedule.
Okay, cool. So now this is just a plug for the upcoming work that I'll be working on. Now as a postdoc, the FEAST, the Fred Young Submillimeter Telescope, is basically a LAT. It's a LAT at a higher site. It'll be on Cerro Chajnantor. This will open high frequency windows, and we'll be observing with MKIDs. These high frequency observations are going to complement SO science as well as other CMB science. We'll be able to characterize dust at a variety of high frequencies and make excellent SE measurements with the FEAST. We'll be using PrimeCam as our first generation science instrument. You can think of it as a small ladder. So it has instrument modules that are SO sized, and we're working based off of the SO design in order to make them right now. PrimeCam will be able to hold 7 of them. And it's a similar design to the LATR, if you're familiar with it, where these are cantilevered off of the 4K plate. Right now, PrimeCam is currently being fabricated, and we're working towards the Fabry-Perot interferometry that will enable our spectroscopic observations, as well as making the first instrument modules. These are going to be tested in ModCam. So ModCam is a first light instrument for CCAT Prime. It will be a single module test bed for PrimeCam once PrimeCam is ready for deployment. It has a DR offset to the side. So whereas for PrimeCam, we have a DR right in the center, you need to remove it in order to swap out your instrument modules. Here we can just swap the instrument modules in and out the back. It can have the SO readout harness inserted or custom readout like we're working with right now. And again, it's compatible with the SO models. So I'm working with Bob at UPenn in order to make the first module. Here's another schematic of it now. We've done dunk tests of the absorbing tiles, the same plastic ones that were modeled for the mold at Penn. And we're currently assembling it. And we're going to be deploying the first light array at 280 gigahertz using MKIDs. So we're currently testing that array. So in the future, we're going to be able to open up these high frequency windows and enable excellent SC science. And in the future for CMB S4, we could potentially put a even larger diameter cryostat holding up to 19 PrimeCam style modules or even more smaller diameter modules on the FEAST at this really excellent high elevation site. So thank you. And I'm really happy to take any questions.
SO planning committee meeting of the next time. So I'll make it really quick. I'd love to hear your take on hot spectral measurement polarized.
I can't hear you. I'm sorry.
Oh, let me get closer. Oh, Brian wants to know prospects on measuring the polarized SC effect someday.
Oh, that's a great question. I don't have any numbers in hand for that. I haven't looked at forecasts for that. It might be kind of just lip service to say it'll get better, but of course all of these measurements are going to be characterizing contaminating effects and enabling multi-frequency measurements to enable those. But that's a good question. I'd love to look at some numbers and forecasts for that.
Thank you. I gotta run.
Brian was just saying he needs to run, and thanks.
Okay, thank you, Brian.
And congratulations.
Thank you.
I got a question.
Yeah.
So I do appreciate you at least showing the SAT on these slides. Know your audience. This isn't even something I've thought of, and obviously it's not our science case. But out of curiosity, would a half-meter aperture telescope even be able to detect a cluster?
I don't think so. We're looking at arc minute scales.
Photons in the beam, but the beam is, well, very smoothed out.
I don't think we'll be using the SATs for any high resolution.
We'll be using it. It's just a question of whether we'd be able to see it or not at all.
I don't think we'll be able to see it. I mean, if you look at Planck, right, in the early plots, the clusters don't show up because it just lacked the resolution.
That's kind of right. We appreciate it.
Well, on a nice thing is that with the feast and these high frequency observations that will help the SC science, will also really help the search for primordial gravitational waves by controlling for the dust that you guys need to be controlled for. So we're helping you.
Thanks. Any question?
Before this talk, have you heard of this Sunyaev-Zel'dovich book?
I read the video.
Nice.
That's not quite.
Yeah.
Um,
They've heard of the SE.
So
You've
I
heard of-
actually, oh,
Great, sorry, I didn't quite hear that.
we were just saying Virginia and Ethan here have heard of the SC effect. So hopefully they got at least, some of the talk.
Kind of the cutting edge.
Yeah. I did have one question on that plot of the Compton Y parameter versus optical depth. I wonder if you just have like a heuristic physical explanation for why theoretically it's a straight line, and like, what would it physically mean if that cluster on the far right is in fact, at that lower optical depth value?
Well, I mean, if we say, okay, the theory's wrong, the experiment's right, then whatever fit we do to this would just be a slightly different model. The model parameters that come out when you do that fit aren't too super drastically different than the parameters that show this line as it currently stands, just because of how the math works. If we go back here to what this looks like in terms of the original model, this is optical depth versus Y. There's some scatter, but basically this is telling you that the higher mass gas is more optically dense. And the relationships that are fit here are to simulations that are taking into account different types of models. So for example, the non-radiative model in green, which seems kind of disparate from the other ones, I understand to be a less realistic circumstance. Like obviously there is radiation, I guess there is radiative cooling and these other things that are happening in galaxy evolution that I'm not an expert on, but are probably present and making this non-radiative case more extreme. So we worked with the AGN feedback model, which is considered to be more realistic. You can tune these parameters and come out with slightly different Y-tau relationships. And so maybe there would be some implication then if the theory here was incorrect and this higher mass spin was indeed where it is currently. So basically the fits that we could make to high signal to noise data would inform the simulations and the physics models there and might glean some insight into the future. But right now we can't say anything strong about that.
Sure. No, that makes sense. Thanks. I mean, yeah, just looking at that, maybe, is there any talk about like different processes are important at different halo masses, so that like that's how you might get this turnover if it really exists?
There hasn't been a discussion on different mass halos having different physics involved. I don't think that would be the main explanation here. I think it would probably be just a difference in, of course, if it's not a straight line after all, yeah, then you're entering some regime that I'm not sure about.
Sure.
Yeah, I'd rather not speculate about different physics that may or may not exist, but it'll be really interesting to constrain with more data.
Yeah, no, that's fair. Okay, yeah, thanks. All right.
Oh, sorry. I
No, go ahead.
A quick question. When you're showing the plots with the circles and the there's that shadow and you were able to see dust.
Yeah.
I missed how you were able. Oh, sorry. A couple slides back, I think. Yeah, these. I was actually confused how you're able to figure out that this would be dust. I guess I didn't fully understand why some values were negative and how you're able to determine that versus the dust values, if that makes sense.
Yeah, definitely. We expect the SC signal to appear as a decrement. meaning, so these submaps are plotted to the average within the annulus, so they're normalized here. So the dark spot indicates a decrement in temperature that is the TSE effect showing up because of the shift in the black body spectrum. So anything that's an increment instead of a decrement at this frequency is probably a source of emission, and dust is a source of emission, which means it would add to the temperature we're seeing rather than take away from it in terms of the SE effect. So when we're seeing a bright spot appearing instead of a dark spot, that's telling us that it's emission and not the SE effect, which is what we're trying to measure.
Cool. Yeah, I appreciate it. Yeah, I totally missed that it was a decrement. Yeah, it makes sense. Cool. Thanks.
Yeah, and it's just at that frequency. So if we were looking at something above 220, we're looking at 300 gigahertz, we would be looking for an increment and not a decrement. So that's why it's useful to measure the SE effect at multiple frequencies, because if you do, you'll be able to learn more about what the dust might be in your maps.
Cool. Yeah. Thank you.
Any other questions from anyone on Zoom? All right, maybe we'll call it there. It's a little bit after noon, so I guess last chance. Questions? Nope. Okay, well, thanks a lot, Eve. This was pretty great. I really appreciate you coming on.
Thank you so much. It was great to see everybody in a semi in-person seminar. That's really neat.
Yeah, it's one of our first ones we've done like this. So.
Yeah.
Well, it's cool to get the gang back together.
Awesome.
Yeah.
All right. Well, good luck with all of the sat epoxying.
Thanks. Good luck with your postdoc.
Thank you. All right. Hope to see you soon.
See ya.
Bye.